Uh, Good afternoon, everybody. Thank you very much for joining me. I was asked by Acqueo to present this webinar on the security requirements in OT environments with a specific focus on the network visibility aspect. And for some reason, we'll go back. Sorry. I'm the EMEA sales director for Garland Technology. We're an American manufacturer of network visibility products, both for IT and OT environments. My own personal background is in both networking and security, having been previously an engineer, a consultant, and in more recent times in a sales role for a number of different manufacturers. So why is security within OT environments such a hot topic? Speed and security have always been the mainstay considerations within IT environments. However, in OT, the driver has always been on safety and 100% availability. Protocols and devices in the OT environment are not reliant on a high-speed bandwidth network, and security was never really a concern, as historically this was always an isolated environment. Today we are seeing a transformation and an IT-OT convergence. The IT and OT environments are becoming connected. IoT device usage is expanding, and remote monitoring management is becoming more normal practice. Given the primary driver of the OT environment was for non-interrupted availability rather than security, this environment, through this convergence, has become a primary cyber criminal target. Once the OT controls for physical equipment are converged with IT computers and networks, the air gap that previously existed between the IT and OT for years is gone. Research shows that malware and cyber attacks will almost certainly be designed to target and penetrate this expanded digital attack surface, resulting in an increasing number of breaches. There are numerous compelling reasons why OT networks are prized targets for cyber criminals. Whilst OT systems do not offer personal data information, often targeted in an IT environment, impacting a critical infrastructure system has huge appeal for state-sponsored and commercial gain cyber criminals. Agendas can extend to holding a critical system hostage, manipulating stock prices, or operating as a competitive agent. People often refer to an organization being a critical infrastructure. So let's first just look at this definition. The USA, NATO, and EU all have slightly different definitions, but in summary, they are all defining the same thing. And that is an asset or a system that is essential to the social and economic function of an economy. Destruction or disruption to it would have a significant impact to the function of the citizens or economy of a country or the EU as a whole. In December 2004, the EU endorsed the intention of the European Commission to propose a European programme for critical infrastructure protection, normally referred to as the EPCIP, whose objective was to protect critical infrastructure in the fight against terrorism. Not only did it apply to the main area of the European Union, but also to the wider Europe economic area. The key pillar of the EPCIP was formulated and published in 2008, and that's the 2008 114 EC, the identification and designation of European critical infrastructures and the assessment of the need to improve their protection. Within this directive, critical infrastructure was initially defined as just energy and transport. Whilst this directive brought focus to the threat of disruption, it did not in itself go far enough. So later, the EU published a further directive in 2016-1148, normally referred to as the NIST directive. This directive defined the measures necessary to achieve a high level of security of networks and information systems, mainly involving essential service operators and digital service providers in various sectors. And the sectors defined were energy, transport, and added to those were health, digital infrastructure, and water supply. However, in this first version of the directive, some problems were found in terms of clarity, as the scope of application was not sufficiently defined, leaving member states with enough discretion in how to implement the requirements, as well as in identifying the entities that were involved. Furthermore, the coverage of the sectors was found to be too limited, as the directive was no longer able to reflect all sectors providing essential services to the economy and society. In addition to the aforementioned, following the digitization of recent years and greater interconnection, followed by a significant increase in cybersecurity risks due to the increase in the use of cloud services following the massive adoption of remote work caused by COVID-19 pandemic, the introduction in our daily life of 5G networks and mobile connectivity technologies and IoT devices, the European Commission has now introduced a new variant called NIS2. For those superstitious amongst us, Friday the 13th of May 2022 would not be an auspicious date to make a significant announcement on the future of cybersecurity, but the European Union did just that. The EU announced a political agreement between the European Parliament and all of the member states on updating the previous NIST directive. The original 2016 NIST directive, whilst contributing to improving cybersecurity, left too many gaps and discretion to individual member states. Ambiguity, lack of accountability, and ultimately fragmentation were the result. Gaps in approaches led to friction and a barrier to trade, and eventually led to more risk to businesses and individuals. This is why NIS2 is so important to the cybersecurity community. There were 4 major gaps that this new directive seeks to close. Number 1 was the scale. First, it significantly expands the scope of application, which is of major importance. Growing interconnectivity, rapid digitization, and ubiquitous connectivity mean more enterprises are becoming important to defend from cyber risk. Critical infrastructure was therefore expanded to now also include banking and public administration, food production, postal services, and waste management. A next major change was in governance. Enhancing security governance and making senior managers in a business accountable for cyber resilience was a major step. Accountability drives behavior. Another thing that was introduced was fines and sanctions. Governance is especially important when combined with increased fines and broadening of the actual sanctions. And finally, incident response obligations. Gaps have been closed and revisions made on incident response obligations. For example, what constitutes a significant impact on an entity has been clarified. Ultimately, disclosure of incidents drives responsibility. As outlined in NIS2, governance at this level can be a good thing for business and the economy. While many will look at these increasing responsibility as a potential cost to their business, building a more resilient digital ecosystem is a strategic necessity. Where GDPR drove up standards in the European Union, it also became a model to follow outside of the European Union. NIS2 has the potential to raise the bar and close the gaps, not only within the European Union, but also outside of the 27 member states. An example of this can be seen in the UK. We are no longer a part of the European Union, but NIS2 is an important guidance for industry in the UK as well. So where does network visibility fit into all of this? Given the NIS2 regulations and the compelling risks of doing nothing, companies are actively seeking and implementing non-disruptive, sophisticated security solutions for their OT environments. Many of these solutions are reliant on obtaining visibility of the OT network, data and devices for functions such as asset, vulnerability discovery, threat detection and response. Those companies that have chosen to do nothing or are playing a waiting game are walking a dangerous tightrope. NIS2 now applies to a much wider spectrum of organizations, and the consequences of not meeting these guidelines before the deadline are extremely costly, with fines of up to 4 million euros or 2% of worldwide turnover. There are also significant business impacts to consider. Downtime costs money, and the loss that there can be in customer confidence in an organization. Maybe it could be in the slowdown of a manufacturing or production process. Whatever security route a company takes, they will ultimately require network visibility. Security solutions are only as effective as the data they obtain. But in the OT environment, there are many challenges. We often find old and dated legacy equipment that has not been touched or patched for many years. Those operating the OT infrastructure are fearful of touching a working environment. The fear of change is a major hurdle. Often the documentation is limited or in some cases non-existent. Nobody is quite sure of the cable types, the lengths. Obviously, there is also this requirement to satisfy the regulatory aspects, but also consideration has to be given to restrictions imposed by manufacturers of their switches and PLCs, etc. And of course, last but not least, there is limitations in terms of the availability of funds to implement the security. There are numerous companies vying for a slice of the OT IDS platform deployed as part of the security stack in an OT environment. We partner at Garland with numerous technology companies, Nozomi, Clarity, Forescout, Rebo, Dragos, a whole host of different companies in that space, SCADA Fence. These platforms all require physical access to the network data. Organizations, whilst recognizing there is a requirement for physical access to the network data, alarmingly often do not consider this aspect during the security tool selection and planning stages. Without secure, non-disruptive access to the data, then those security tools simply cannot satisfy the need. Unfortunately, some IDS vendor salespeople will tend to focus solely on their own platform and almost dismissively suggest that data can be simply obtained from switch, spans, and mirror ports at no additional cost. But more consideration must be given to the actual obtaining of the data from the network. The reality is there are two methods to gain visibility of the network data: span mirror ports on switches or network taps. Span requires reconfiguration of the switch to designate a port as a mirror port, whereas a network tap is an additional hardware device that is connected into the network link. This dedicated device is invisible in the network and will make 100% copy of the data passing across that link. Taps can be passive devices or active components with internal fail-safe technology that ensures the integrity of the network link is retained in the event of a power fail, etc. Taps have a number of operating modes: breakout, where east-west traffic is mirrored out of one monitor port and west-east traffic is mirrored out of a second port; aggregation, where east-west and west-east traffic is combined and mirrored out of a single port; and then we have regeneration or span taps, where traffic can be fed into one port and then copies mirrored out of the remaining ports on the tap. So why should somebody consider using taps rather than span? Firstly, often span ports are simply not available. Some of older generation switches don't have a span capability, and some have no free ports to use for span. The next consideration is the span port media. Is the media type suitable? Is it do you require a fiber link and the span port can only generate a copper link? As mentioned previously, the fear of change. Maybe switches will need patches. What might be the impact of making patch updates to the switches? While span might appear to be a simple thing, there is a reliance on reconfiguring each switch. Once they are reconfigured, then performance monitoring of that switch is essential. And each time a switch needs replacing, consideration needs to be given to reconfiguring the span port correctly. Span, as the name suggests, stands for Switch Port Analyzer. And as that name suggests, it was developed as a troubleshooting tool. It was never designed to be a constant security monitoring facility. And some manufacturers insist that span is not used for that purpose, whilst others in their documentation highlight the fact that a span port is possible to drop packets. The other thing that must be considered is that span port is actually a switch port and therefore an intrinsic part of the operational network. It has both a receive and a transmit facility. After all, it is a switch port. By opening up a switch port for span, you could also be opening up a security vulnerability as you're providing a mechanism to inject traffic back into the network. It also has an operating system. What better way to disrupt a network than a malicious attack on the actual switch? Some industrialists could use the span. And last but not least, there are performance considerations. A span port will change the timing of packets and will discard packets in error. They will also discard packets in oversubscription situations. If the configuration of a span port is simply to mirror on a one-to-one basis, so a single port mirrored out of another port, then the span port will not drop packets. But in older generation switches in particular, when you configure the span port to mirror data from multiple of the switch ports, you are liable to drop packets, even if the utilization level on the OT network is low. Designs of these switches typically use a shared memory architecture, and this becomes a bottleneck and can therefore lead to dropped packets. You will also find that some packet types are simply not mirrored, another great method for an attacker to avoid detection, by the way. The point I'm highlighting really is that best practice is always to use a network tag whenever you can. You never need to reconfigure or touch the switches. They will guarantee 100% packet availability and can provide monitor ports for other tools if you require. Garland taps are also unidirectional data diode devices. This ensures that no traffic can ever be injected back into the network through the monitor ports. And last but not least, while there can be a small additional CapEx cost to purchase taps, the actual operational cost is much less. These are hugely reliable, dedicated devices that once installed, never need to be reconfigured or patched again. The Purdue model, formerly called the Purdue Enterprise Reference Architecture, PERA, is a structural model for industrial control system security, concerning physical processes, sensors, supervisory controls, operations, and logistics. Essentially, the Purdue model guides micro-segmentation security policies by grouping assets into zones that share common security requirements. Conventional IT segmentation falls short in an OT environment. For decades, we relied on robust perimeter security to track north-south traffic communications at the network level. However, conventional IT segmentation with complex VLANs and firewall configurations takes time to build, and there's little tolerance for prolonged downtime in OT environments. IT firewalls also can't provide 100% visibility into which set of packet exchanges are authorized in an OT environment. With the increasing sophistication of cyber attack techniques, micro-segmentation is emerging as a viable solution for reducing OT attack surfaces, although currently connectivity to external systems continues as the overwhelming root cause of security incidents. Micro-segmentation affords granular visibility at the workload level and provides the basis of zero trust security. In the Purdue model, the industrial network is divided into 4 zones and 6 levels. A 5th zone, the safety zone, is only relevant for nuclear power stations. Level 5 is the internet zone, sometimes combined with level 4, and is considered the public-facing level, which comprises corporate level web and email servers, etc. This is typically where attacks originate. Level 4 is considered as the enterprise zone, and as said previously, often looped in with level 5. This is where IT infrastructure is located, from operational management to printing and phone systems. It is considered critical to segment this level from the ICS environment. And this is typically where you see a firewall. Now we have the industrial zone. Level 3.5, this optional level separates the ICS networks from the corporate environment. This is where we usually find role-based access control, etc., where users are given access based on their roles. This level is typically segregated from the enterprise levels, limiting direct access to the internet. Level 3 is responsible for managing the ICS SCADA environment, including historians, workstations, the DNS and the DHC servers. It communicates with the OT levels and with the corporate levels through the DMZ zone. Level 2 is the OT-ICS zone. This level includes the human-machine interfaces and the engineering workstations that control the RTUs, PLCs and DCSs. Communication with the corporate levels again is done through the DMZ zone. Level 1, this is where the RTUs are located, the PLCs and distributed control systems reside. These control-based appliances are usually not connected above level 2. Level 0, this includes the field devices, the solenoids, valves, motors, and smart meters, etc. And as I said previously, a safety critical zone is an optional zone that only pertains to nuclear power plants. In order to properly segment ICS networks, industrial organizations must determine how, what, and why systems are communicated within their networks. A proper understanding of asset configurations and data flows is crucial to knowing how to segment network zones. In particular, asset inventory management is an important first step in securing the integrity of an OT network. To protect what you have, you must know what you have. Typical solutions are incorporated into the IDS systems of Nozomi, Clarity, Forescout, Dragos, etc. And then there are companies that focus purely on the inventory aspect, such as Awen Collective. But what about firewalls, you ask? Although conventional or even web application firewalls are useful in an IT environment, they simply don't provide sufficient security within the OT space. So it comes down to combining IDS monitoring solutions together with data diodes. So where do TAPs fit into the Purdue model? In the OT environment, we tap at layers 1, 2, and 3. And we can also tap, obviously, in the IT environment at level 4. It's important to always look where data flows and tap those paths. Remembering that taps are invisible once installed. Data is mirrored out via a unidirectional port. They will include fail-safe to ensure the network link is not disrupted and can be mounted in a numerous ways. Either standalone, in a 1U cabinet, or on a DIN rail. Garland taps provide all this functionality, plus they have ruggedized enclosures and support extended operating facilities like extreme temperatures. In this example here, we are tapping switches on a redundant Ethernet ring and then feeding those monitoring feeds to 2 IDS platforms. In larger networks where there are numerous taps with monitor feeds, there is a need to combine this monitored data together. Whilst some IDS vendors provide the option of installing multiple interface cards into their platform, this is not ideal. Perhaps each monitor feed needs to be highlighted with a VLAN tag to say where the feeders come from. Perhaps there are other tools that would benefit from this same monitored data, such as a network monitoring tool or a troubleshooting tool. What happens when there is an update to the network, perhaps a speed or media change? Does it then mean changing the interface within the IDS platform? All of these considerations should be given. Best practice is to use an aggregation device, commonly called a network packet broker. Using this device, the monitor feeds from the taps, and indeed, if you choose to use SPAN ports, can be fed into the packet broker. These feeds can then be aggregated together and fed out of 1 or more ports to the security and monitoring tools. Garland have a hugely scalable family of products, from very small form factor to large chassis devices. We support speeds from as low as 10 meg right up to 100 gig, obviously not required in the OT environment. Advanced functions can be performed on data, such as removing duplicate packets, adding timestamps or VLAN tags to indicate where a particular packet has come from. All of this can be accomplished through a very easy to use GUI interface or a command line interface. In this OT environment use case, we are tapping again the Ethernet ring, but rather than feed the monitor feeds into interfaces into a single IDS, we're taking those feeds into a network packet broker, which can then provide a feed to the IDS system, but also provide the same data to other tools. In this example here, a deep packet inspection and the CM system. To summarize, since 2011, we have designed, built, and deployed solutions within OT environments, and we continue to do so today, developing new products specifically for this market segment. I have not dived down into the depths of our product portfolio, rather I seek to give it an overview. We're quite happy to organize sessions on a one-on-one basis outside of this webinar. Our TAP portfolio is the widest in the industry. We have TAPs in pretty much every conceivable environment, from Humvee military vehicles, testbed cars, Royal Navy ships, locomotive trains, wind farms, nuclear power stations, water treatment plants, flood defense systems, pharmaceutical manufacturers, car paint shops. Ultimately, it's a big market segment for us. We have a range of products that are specifically targeted at this particular market segment. And together with our partners, we are here to assist you. I wanted just to leave you with some takeaways. Please visit our website. We have a host of different white papers and blogs on our website. These are just a few, but there's a lot of material on solutions in the IT and the OT space. And with that, I'd like to say thank you and take any questions.
Okay, thank you, Ross. Thank you very much. So, jeder, der Fragen hat, bitte in den Chat stellen. Ich werde die einzeln auch vorlesen. We will start with the first question. The first question was, you mentioned a data diode tab. Can you explain this? What is a data diode tab?
Yeah, sure. So by a data diode tab, what we are referring to is the fact that if you're tapping a network, then on the monitor ports where you're mirroring the data out, a data diode tap inhibits the transmitting of data back into the monitor ports and into that network. We have this, what a lot of people use some of our taps for is on where they've chosen to use a spam port because of the risk of opening up a vulnerability, and indeed some regulations prohibit the use of a spam port without some form of protection on the spam port to prohibit data going back into that spam port. We can use one of our spam taps. So you connect the spam port of a switch to a spam tap, which just provides unidirectional data transfer. So you cannot send data back into the spam port of the switch. It's physically impossible. It's actually air gapped.
Okay, great. Okay, the next question is, do you have all, because you were mentioning a lot of diagrams, the physical things, do you have a virtual tap or something like that as well?
Yes, we do. So we have a virtual tap solution, which was specifically designed for the OT environments. And it was specifically designed for a particular customer where the regulations in that country wanted a data diode OT tap design. With a typical virtual tap, it is possible. It's two-way traffic on a virtual tap typically. What we designed is an OT tap that can be installed in a virtual environment that is purely unidirectional, can only send data out of that virtual tap. So we do have a tap for that environment.
Okay, great. And the next question was, can a packet broker also act like a data diode tap?
No, it cannot. In itself, it don't. A packet broker has bidirectional communication facility on the ports, so it cannot operate as a true data diode.
Okay, and the last question I got so far is, what's the difference between the aggregation data diode tap and the packet broker?
An aggregation data diode tap and the packet broker. The packet broker can provide more sophisticated functionality than the aggregation data diode tap that Garland manufacture. The aggregation data diode tap that Garland manufacture has fail-safe connective capability on the network links. There is no filtering capability. It simply aggregates the data together and passes them out of one or two ports on that aggregation device. So you can aggregate 4 tapped links out of 1 or 2 ports. You can daisy chain 2 of them together, so you can ultimately take 8 tapped links and aggregate those out of a single port, or you can use a span variant where it would take 8 span feeds and you can pass that out of 1 or 2 port, but it's purely aggregating the data together. It has no other intelligence within the device. In a packet broker, we can do things like add filters and filter out certain traffic types, although typically that's not required. We can add VLAN tags. We can direct the traffic out of any number of ports. We can load balance that traffic across multiple ports. So if you wanted a redundant configuration with 2 IDS platforms, we could balance the traffic across a pair of IDS platforms. So it's a much more sophisticated device.
Okay, thank you. I think there are no questions at the moment. So thank you, Ross, for presenting. Ich sage auch vielen Dank an alle Zuhörer und Zuschauer für die Folien. Wenn es noch Fragen gibt, melden Sie einfach bei uns und ich wünsche allen noch einen wunderschönen Nachmittag. Vielen Dank. Thank you, Ross.